All right, so what we're going to do, we didn't do the sine over x one, did we? Let's look at that example as well. So it says final value of the limit using a table and then confirm graphically and algebraically. So go ahead, take out your graphic calculators and type into y1 sine of x over x. And in your table, since we're looking at the limit as x approaches 0, this is the case where you're going to have negative 0.1, negative 0.01, negative 0.001, 0, 0.001, 0.01, and 0.1. And as we look at those numbers, what can we tell or what can we justify that it is approaching? Yeah, the number 1, right? So we say, based on the table, the limit as x approaches 0 of sine x over x is equal to 1. Go ahead and look at the graph. So go ahead and change your view so you can see this as a graph. So what does it look like is happening on that graph? What does it look like a function is doing as we look at the graph of it? It's kind of doing what? It's almost like very flat on the outside, so then it like peaks up and goes to the number 1, and then like kind of does the same thing on the other side. So in order to look at something like this algebraically, we have to be able to come up with a way to get x out of the denominator. And this isn't something like we could do with the factoring where we can cancel them, right? So in order to solve something like sine x over x algebraically, we need what's on your next page of your notes, which is called the sandwich theorem. So what we have to do is we have to essentially, in order to look at something like this algebraically, is to sandwich it between two other functions that we can find derivatives of, or limits of. So if we cannot find a limit directly, so by directly, what that means is if you take the number, so a direct limit is when we take the number and we simply plug it in. So direct substitution would look like something like this. And we know that we can't do that because we know we cannot divide by 0. So we cannot do this through direct sub. So then we go and we look at what we call the sandwich theorem. So what that means is if we cannot find it directly, we are going to come up with a way to find it indirectly. The indirect method we use when we cannot get that variable out of the denominator is called the sandwich theorem. And what the sandwich theorem does is it says we're going to find two functions that we can sandwich that middle function between. So we're going to find two other functions that we can sandwich our function between. And what it means by sandwiching between them is it means the range. So what we're going to do is basically find two functions whose range is going to limit our current range. So, for example, we're going to say the limit as x approaches c of g of x is equal to some number L. So in this case, our g function is that pink function. So g is the pink function, or in your case, the very squiggly one. So we are going to sandwich g between the blue and the green. The blue and the green are the f and the h that g is going to sit between. And right now it's kind of like, what are you talking about? Once we start to look at the math behind it, it should start to like make a more clear picture. So what we're going to do is a calculus version of a proof. So you did proofs in geometry. We're going to do a calc version of a proof to prove why this is true. So we're going to use the example that as we go to 0 of x squared sine 1 over x and prove that it is equal to 0. So the functions that you see graphed at that top are these functions. You have g of x being x squared, where's this case? It's definitely sine in your graph. That's okay. It doesn't matter because we know cosine and sine are essentially the same things, just shifted. So we know that sine of x lies between what? What is the domain of sine x? What is sine's domain?
Negative and positive. Domain's the x.
Yes. Yeah.
Just for all.
Yeah. So the domain is all. And then what is our range on a non kind of shifted side function?
Negative 1 over 1.
Perfect. So we know and that's going to be important to understand the domain and range. So we know that the range of sine is -1 to 1. So what we can do is we're going to use something called the triangle inequality statement. And the triangle inequality statement basically says, kind of if you go back to geometry, that two sides multiplied together had to be greater than the third side. That if you picked any two sides, that had to be greater than the third side. And you couldn't have one side that's super, super long idea because then they wouldn't be able to connect. So essentially what we're doing is we're saying that, okay, the absolute value of this function cannot exceed -1 to 1 because of the range. And so what we're going to do is we're going to say, okay, the absolute value of x squared sine 1 over x is the same as looking at the absolute value of x squared times the absolute value of sine 1 over x. How can we know that this is true? What do we know about x squared? It's always positive. So when you have something that is always positive, you can take an absolute value and break it into two absolute values because this really meant nothing having an absolute value here or not here. Because x squared is innately positive. And then what we're going to do is we're going to say that this has to be less than or equal to the absolute value of x squared times what is the largest value for the range of sine? 1. So instead of looking at the absolute value of this, we say, okay, the largest possible point is 1. We can't do that so much with x squared because x squared, continues positively forever. the absolute value of x squared times 1 would then just simplify to x squared. Because the absolute value really has no change and 1 has no change. If we wanted to sandwich that function then, what do we know about the opposite side of this? If the right side has to be less than or equal to x squared, the opposite side would what?
So it would be greater than -1.
Exactly, it would have to be greater than or equal to x squared times a -1. So what we can say is because the highest point is 1 and the lowest point is -1, this function has to live between negative x squared and positive x squared. And what function has to live there? Yeah, g of x. I'm literally it's making me so angry. One more time. All right, so if we know it has at most a negative x squared and at the greatest a positive x squared, what is our limit looking for? Like, we're looking for what's happening where? Yeah, at 0, right? So what we could do is we could say, okay, we know it has to live between these. Let's look at the limit of this and the limit of that to see where this would be. So if you look at the limit as x goes to 0 of negative x squared, we can simply plug in 0. 0 squared is 0. Negative 0 is, okay. So x squared goes to 0. The limit of negative x squared goes to 0. Therefore, the limit of that middle part must also go to 0. Because it can't be greater than it. It can't be less than it because it lives in the middle of it. So we say, therefore, by the sandwich, well, I'm just writing so it doesn't matter. So therefore, by the sandwich theorem, the limit as x goes to 0 of x squared sine 1 over x must also be 0. Good? Yes?
So you mentioned how the range was between -1 and 1. But how do we know that for certain this function or the extra change?
So sine of 1 over x, even if you put in the max and the mins for x, that 1 isn't going to change the range being from -1 to 1. Only because the sine answer you get as an output can't be greater than. So think about all the functions you can plug in for 1 over sine. Like they're all going to be smaller than -1 positive 1. Does that make sense? Because the x squared part of it doesn't matter. We're not talking about the range of x squared. We're only talking about the range of sine x. Because x squared's part of my exterior range. Yeah, that would be infinite. Okay? Let's look at simplifying algebraic expressions that don't need to be sandwiched. So we already kind of hinted at a couple of them the other day when we did the table. I showed you how to do the factoring ones. I showed you how to do just like the regular plugging in. And then what we're going to do today is add one more type, which is the conjugate. So we're going to look at how do you multiply by the complex conjugate. So here are the 4 steps we're going to follow when we want to simplify limits. The very, very first thing we're going to do is try to substitute into x, which means if you get a limit, you plug it in. The very next thing you're going to want to do is if I plug it in and I cannot simplify or I cannot get an answer, then we are going to factor. So plug it in. If it doesn't work, okay, try factor it. So when you factor, you're going to try to cancel something from the numerator to the denominator. Then plug in x. If you get a numerical answer, awesome. When you factor and simplify, if you get a number for the numerator and a 0 in the denominator, so that would be like a number here, but a 0 here. Anytime we try to divide 0 by a number, for a limit, there is none. So anytime you get number over 0, there is no limit. That is DNE. A number over a 0 is DNE. A 0 over a 0, or a 0 over 0 is what we call the indeterminate form, and that's when we're going to continue to try to simplify. If you get 0 in the numerator and the denominator, we call that the indeterminate form. So 0 over 0. That means, or that tells you, keep working. There is a limit. Keep working. There is a way to simplify. So the very first example is the limit as x approaches 5 of 2x squared minus 3x plus 4. That's a polynomial function. We know by definition that polynomials are continuous. This is a specific type of polynomial. What type of polynomial function is this? What do you call it? Squared function. Quadratic. It wasn't like a trick. It was like, okay, so this is a quadratic. Quadratics are continuous. Domain is all reals. Therefore, you can plug in any limit. The limit you plug in is also its x value. So we're going to look at the limit. Anytime you have a limit, you must write limit. So when I plug it in, I have to write the limit until I get a numerical answer. So what that means is on your paper, if you have this, you can't put equals until you plug in all of the numbers. So once you've plugged in all of the numbers, then you don't have to write the limit anymore. So I have the limit of 2x squared minus 3x plus 4. So you just want to be careful. You can put your equals. Now plug in your numbers. So the minute you plug in your numbers, you no longer have to write the limit anymore. So you get 2, 5 squared minus 3 times 5 plus 4. Again, we're in calc, no calculators for something like this. This would be a mental math problem. Make sure you follow order of operations. You get 25 times 2 minus 15 plus 4, which is 39. Okay? In example 2, don't get tricked. Sometimes when we see factoring problems, we immediately think, oh, I got to factor that. That's not always the case. Your first decision is to plug in the number. So the very first thing we're going to do is plug in -2. So you get -1 over 11. Okay? It's pretty straightforward. Not very complicated. Number 3, you have x squared minus 1 all over x minus 1. If you do what you're supposed to do, which is to plug in directly to start, then you'd say, okay, the limit as x approaches 1 of 1 squared minus 1 over 1 minus 1 gives 0 over 0. 0 over 0 is the indeterminate form, so that tells me, okay, I can do something to make this problem work. So then I would say, all right, the limit as x approaches 1, I'd look at that top quadratic and say, what can I do? Well, it's a difference of squares. So a difference of squares factors into a minus b, a plus b. So you get x minus 1, x plus 1. What happens now is that x minus 1's cancel. So the limit as x approaches 1 of that original function is equal to the limit as x approaches 1 of x plus 1. So then what we do is we plug in our value, and we get that the limit as x approaches 1 of x squared minus 1 all over x minus 1 is 2. And example number 4, any thoughts on what we want to do to example 4 after we directly plug in? So again, can't we already see what's going to happen if I directly plug in? We know for sure there's a 0 in the denominator. What I need to do is check that the numerator is also a 0 and that this is not a DNE case. And again, what we'll notice is that 3 squared is 9, 9 minus 9 is 0, so we get 0 over 0. How could I simplify this? What could I do? What would your first thought be? Without changing the problem at all, what can I do? Yeah?
I separate the tops
Okay?
into 3 plus x squared over x minus 9
It's even easier than because separating them isn't going to help me with canceling anything. When you have something squared
I split
in your
out
top,
and then combine.
yep. If you FOIL out, never square a denominator, but always square a numerator. So never square the denominator, but always square the numerator. factor out through FOIL that top part.
And then you can pull on which is the numbers to cancel.
Yeah. So if you FOIL that numerator, you get 3h in the middle twice, a 9 on the outside, and an h squared on the outside.
Would the following students please report to the office? Jalen Schober, Sarah Harriet, Natalie Buns, Sarah Green, and Ashley Navarro.
Yeah, we can pause for you, dear. I don't want to do this without you. So if it's going to kill you guys, you can finish this problem and let me pick up the next one for you guys. So at this point, our 9s have canceled. So we have the limit as h approaches 0. Combining like terms, we get 6h plus h squared all over h. So we know that if we have an h and an h squared, we can GCF that out. So we get the limit as h approaches 0. Take out that take out a GCF of h. The h's on the outside cancel. So we get this is equal to the limit as h approaches 0 of 6 plus h. Now I don't have any issues with the denominator, so I plug in my 0. 6 plus 0 is 6. Therefore, the limit of this function is 6. So again, that's how we use algebra to help us do our limit. So again, I hinted for example number 5 the other day that this is the case where we're going to use the conjugate. So we're going to use the complex conjugate. The complex conjugate is simply, I can't write, so we're just going to follow along to what I wrote last year. The complex conjugate is taking the crazy part of the radical in the numerator and multiplying essentially by its difference of square. So essentially when we call something a complex conjugate, we are multiplying by its difference of square. So I'm pretty much making a perfect setup to cancel those middle terms. So if you think about a squared minus b squared, that's a minus b, a plus b. So in this case, we're calling the a the radical, and then the minus b is the number. So what we're doing is we're setting this up to cancel out those radicals. So we're going to multiply it by the exact same radical and then the opposite sign of whatever the number part is. Because what happens is when you multiply a radical times a radical, the radical goes away. And you're left with like whatever that stuff is underneath. So you get the stuff underneath. The middle terms will cancel because they're total opposites. I'll be like minus a number radical plus a number radical. So then you'll just be left with minus that number squared. And you'll see what it looks like when we work it out here. So again, you're going to FOIL both of these essentially. So when you take the square root times the square root, they cancel. And you are left with the limit as t approaches 0 of t squared plus 9. The middle terms are going to cancel because it's a difference of squares worked backwards. And then you multiply the last two numbers together. So negative 3 times 3 is negative 9. What?
And with 1 over 6 as the limit, you could plug in 0. That point.
What?
Never mind.
Okay.
Because I got to the step where you are, so 1 over this t squared plus. But then when you plug in the 0.
Did you cancel your t squared?
Yeah, I already got those. Yeah.
So you're here.
I'm right there, yes.
Okay, so plug in a 0.
Gives you square root of 9, which is plus or minus 3.
Not plus or minus.
Or
Or is it plus or minus?
minus.
Because you only do a plus or minus if you're getting rid of something squared.
Oh, Okay, but if you're taking a square root,
Yeah, because
it's just 1 over 6.
exactly. He asked me an algebra question. You're good. So is everybody okay with this so far? We see how we multiply by the conjugate. We get this. And then what's nice is the positive and negative 9's cancel. And then the t squareds over each other are left, so they cancel. So now you have 1 over, essentially, the original numerator, but a positive 3 instead of a negative 3. Once I get a 1 up here, I know this is a number. So now it's the difference whether it's a number over a number or a number over a 0. So we're going to try one more time to plug in that 0. So when I plug in my 0, I end up with 1 over 3 plus 3, which is 1/6. So once you're good with that, go ahead and look at the next one and start to factor it out. Because again, we can immediately see that when I plug in a positive 4, I get 0 over 0. So go ahead and set up the GCF of number 6. And factor your denominator. So yes, we're getting a plus or minus here. We only have a plus or minus when we have something squared and we take a square root. We aren't taking a square root if the square root already existed. So like if you were trying to take x squared and solve for it, then you take a square root and then you have to put the plus or minus. When the square root is given, we don't put a plus or minus. Okay, so what's nice is both the top and bottom factor nicely. So if the limit is x approaches 4 of x minus 4 over x minus 4 times quantity x plus 1. The x minus 4's cancel, and you get the limit as x approaches 4 of x over x plus 1. So once we've simplified as far as we can, we plug in. If when we plug in we get a number, we are happy and we are done. And the very, very last one. So we have 2 separate fractions right now. In order to add or subtract fractions together, what do we have to do? What do you have when you have to add or subtract fractions? What comes? A common denominator. So go ahead and set this up to create yourself that common denominator. So we have the limit as t approaches 0. The left side, if you look at the original though, this is 1 over t minus 1 over, take out a t, and you get t times quantity t plus 1. So the left side is really only missing the quantity of t plus 1, and the right side already has the t. So you only have to alter the left side by multiplying by t plus 1 on top and bottom. So now that I have a common denominator, we get t plus 1 minus 1 all over t plus 1. So the 1's cancel. Yep, and then after you cancel your 1's, we'll notice we can also cancel t over t. So we got limit as t approaches 0. It's not a 0 up top, it's a 1. T over t is 1 over t plus 1. Now I can plug in, and I get 1. So it's easy. I like them because they work out. Okay, we're back in your book. We're going to page 66. So some of these, we didn't do 38 because we did 37. We did the odds up in here, right? So
I did the odd from 19 to 22.
because they were the algebra. But I just gave you 14 and 16, so it's okay. Yeah. So the only bad thing is you guys can't check it because I've changed them to evens. Because we did like a lot of the odds already. So we'll do 14 to 30 evens, 38, and then that 64 to 70 will be your first look at some AP questions.